Hello, welcome back. Today we're going to be wrapping up memorizing transformers. So we're going to take all of our individual pieces, all of our individual classes, and we're going to stick them together into one model, and we're going to run the model. So this is a very rewarding day. We finally get to put all of our work together and start actually running the model. So before we get to that, there's a few things. So I've imported kind of the regular libraries here. And we have a few kind of things to fix up and add that we were putting off. So first up is our relative position class. So we need to make a slight modification here to account for recurrence. So we built this before we incorporated the XL memory style recurrence. So the positional embeddings get added straight into the attention scores. So we compute QK and we add them straight on top. And we made this positional embedding scheme for square attention matrices. But now, of course, we've incorporated recurrence, so they're not square anymore because we're concatenating old memories. So our attention matrix actually has to adjust to that. It has to adapt. So we need to make our relative attention class adjust for these recurrence relations. And here we've done that here. And I'll show you kind of what this means in a little more detail. I'm just going to pull out the code here and show you. If we say we have a sequence length of 5, then basically what we had before was something like this. That was our relative position embedding matrix. And each of these indices would go and pull out one of the actual weight embeddings. And that's what would correspond to the 0th position, the 1st, 2nd, 3rd, -1, so on. So here, because we're concatenating old KV vectors with the new ones, we're just going to double the length. So this becomes, instead of a square matrix, it becomes sequence length by 2 times sequence length. So we're going to use this. You could argue, and I'm not exactly sure about the details of how this works, and I'm not sure, I haven't found much research or anything showing what the proper way to do it is, but you could alternatively do something like this, where here the 0 begins basically where our first original KV value would be, and the past would all be old KV values. So you could do something like this, depending on where you want the 0th lookup embedding to be. But for now, we'll just use this. Okay, next step is to make some modifications to our KNN XL attention class. Now, we also have to, of course, modify our XL attention class, but I'm just going to show it to you once here, and then off camera, I'll essentially revise the original XL attention class. So in particular, we have a few things to do. We need to pass in positional embeddings, and these will just get added on top of the QKs, and we've even earmarked a part of our class where that code will go. We need to normalize our KV values, which I'll talk about as we modify it. And we need to add dropout. So that's something we've put off, but it'll definitely go in this class. It'll come up another place in our feed forward layer. And there are kind of mixed signals about where exactly you should put dropout for kind of best practices. But we'll start with these 2 places. So let's go ahead and modify the KNN XL attention class. First up is we're going to add the KNN in here. So before we just passed it in through the forward pass, but it makes sense to pass it in just at initialization. We'll add that, and self KNN will be KNN that we've passed in. And we also are adding here dropout. And we need to make sure that we also add self dropout. And the dropout that we pass in is just the probability of dropping a weight. So we've just set it to 0 here, but it can be passed in when you initialize the model. And just as a note, dropout is turned off when the model is in evaluation mode. So during training mode, dropout is automatically on if you kind of have initialized it so. But during evaluation, it automatically turns off, so you don't have to worry about building in any switches. It's just a nice feature in PyTorch. Okay, let's see. Next up, let's normalize the QK values. So why are we doing this? Let me put it in here. Remember that as we feed more data into our model, the model is always changing. So we'll feed some data in, and you could feed the same data in at different points through the model's training stages, and the outputs at the same layer would look very different because the weights are always changing. And so this poses a problem when it's time to do something like search and retrieval, because maybe you've embedded one piece of text at one stage, and later you have a query that in theory is very relevant and should return the embedded keys that you've already stored, but the model has drifted so much that your embedded query no longer really matches the keys you're trying to retrieve. So this is just a general problem of the model drifting and trying to keep embeddings relevant to one another. And the solution in the paper here is to just normalize the queries and keys. And this is in section 3.2 of the paper. So we normalize queries and keys. So every retrieved key will be normalized, and every stored key will be normalized. Remember that we don't look up the values. The values will just be along for the ride. And similarly with queries, every query value that we're searching with will also be normalized. And according to the authors, this does something to mitigate the problem of model drift. So we've put in queries and keys normalized. Okay, now we can add in our relative position bias. So we pull out the shape here. We can actually do it here. And it's really as simple as this. If we have relative positions, you literally just add them on top of the QK that you've created. It's that simple. And we need to make sure that in the forward pass, right, we need to make sure that we are passing in relative positions. And we no longer need KNN in the forward pass because we're initializing with the model. And we can set this as a default to none. There's our Excel memory, great. And let's see, dropout should be the last thing that we need to do here. And this comes after softmax. And we've already stored this and initialized it, so we just call self dropout QK. And that should be it for finishing up our XL attention class, rather KNN XL attention class. And so, where appropriate, we'll make the exact same changes to our regular XL attention class. Okay, let's start building the whole model. So, from the paper, we have some idea of what the architecture is. So they've said the input is tokenized, the tokens are embedded into vector space. The embedding vectors are passed through a series of transformer layers, each of which does dense self-attention followed by feed-forward network, decoder-only language model, causal attention mask, and the tokens of the last layer are used to predict the next token. So there's a lot left unsaid in the architectural details. There's really not a lot to go on. So we can do a few things, which is go through the paper and really comb through details and make sure we're getting everything. The best idea here, and this is so often the case, is just that the paper is underdetermined. They don't want to spell out every detail of kind of a standard decoder transformer architecture. So you go to the code and you look at what they did because you want to replicate their results pretty closely. Beyond that, you can assume everything left unsaid kind of follows the most standard implementation of a decoder model. And even though this paper is only 1.5 years old, the standard implementation of what you do is kind of best practice changes a lot. So we'll use some kind of combination of what's good now and what was good then. But these won't be any kind of major differences that will change the performance of our model. So where do we really start? It helps me, when I'm building this kind of thing, to make a very, very basic map. So sort of like a pseudocode map. And this map applies pretty generally to almost every large transformer network that you would build. So we have some raw text, we feed it through a tokenizer, get the token IDs, and we feed that through an embedding. And then we have a block that is attention and feed forward. And after all those blocks, we have an output layer where we take our embeddings and we put them back into token IDs. And then we have a loss function. So this is a very basic map, but it sort of serves as a checklist and a guide as we start to build our model. We can start with blocks, and while we're building this, there's a few things for our specific model that we need to keep in mind. And this is really just how things are passed in and held onto. So the KNN aspect of our model, as we've seen, should be pretty self-contained. Inside of the KNN XL attention class, we really query and retrieve kind of without need for anything else. Like, you don't need to pass in anything besides the KNN. There's no real work either in the training loop or in the larger model that needs to be done. That should be okay. XL memories, on the other hand, we'll have to manage both from inside the model and the training loop because we want to hold on to them at each pass. They want to be detached from the graph, the computation graph, so we don't want to backprop into them. So we'll have to do a little management around that. The last thing to keep in mind as we build this is what happens if we're feeding in the first chunk or the first segment of a document. So in that case, there are no previous XL memories and there are no KNN memories. So we just need to make sure that there's a switch in place that says, if neither of those exists, we can still function normally. And those are the main kind of considerations specific to memorizing transformers that we'll keep in mind as we're building this. I have a few kind of things to say before we start building this. In general, when you build the model and you put all of these pieces together, it gets pretty complicated and things will break a lot. And that's just a fact. There's no way around it. And there's not even that much insight I can provide. It's just make sure everything is plugged into everything else. So I do have some tips that can kind of help keep you on track. And one, as we've just seen, is build a pseudocode version of things first. And this will help you, instead of maybe diving in and building one component and then realizing, oh, but once I incorporate the other bits, I'll actually need to completely reconfigure how that works. So you won't have to go back and rewrite things. So if you have a good pseudocode version, you'll realize early on what kind of the major architectural changes or design patterns you'll need are. In tandem with that is build the simplest version possible and then add complexity in. So, for example, when we were building these components, I left out things like dropout and didn't pay much attention to scaling and relative position embeddings. Basically, get the most functional early piece first, and then you can add the complexity in. And it's much simpler than trying to basically have this giant laundry list of every single thing that goes in and try testing that. Another tip is to keep a checklist, and I certainly do this. As I've been building this and as I'm going to build the model itself, there are just things like, oh, okay, I need to make sure that I add in layer norm. Where exactly does dropout go? Let me look at some papers and figure out where the best places to put that are. Relative position, sizes, weight initialization. So there's just a giant checklist of things. And as you build, you can make sure that you're hitting every one by just checking them off. Because it's very easy to forget something. And then you wake up in the middle of the night and you go, oh, I never put that in. And you have to, in the morning, restart your model. And the last is definitely to test. So test the individual components and build some tests to make sure that everything is plugged into everything else. And so this is just, all of this is just good software development advice, but this one is particularly important for large models. So errors in large models can be extremely subtle. In many other areas of software development, if something doesn't work, it will make itself known very clearly. But here, it's often the case that the model will train, you get reasonable looking numbers, but in fact your position embeddings aren't plugged in, you just forgot to plug them in, and so you're basically missing a key component. And so you'll just be, your performance will be off by a few percentage points, but it's not obvious that you're missing a major component of your model, for example. Or you are, from personal experience, accidentally reshaping or reviewing instead of transposing one of your matrices inside of your attention. So your attention is definitely wrong, but it still learns something and it still runs because all of the shapes and the tensors match. And so it's just one of these subtle bugs that is very hard to catch. So the advice here is to test early and often and as you build to make sure everything is plugged into everything else, because it won't necessarily be the case that when something is going wrong, it shouts, "This is wrong." So test these components. Okay, so let's start building. To me, when we look at our kind of pseudocode plan, it makes the most sense to build the block first. We'll call this component the block. And so we'll build the block, and then after that we'll build the model, and we kind of compile a certain number of blocks for each layer. And then of course we'll build the input and output. But for now we can just build this, and the pseudocode helps us a lot. It's already a very good, clear map. So we need to build a block, and kind of the main difference here is that we need to build a switch such that we can call KNN attention or plain XL attention. So I've already built this, and I'll just talk you through it a little. So here there's just a switch to say KNN by default is none, and then as we're building the model, if we pass in KNN equals true, or that could be a flag, or we could pass in the actual module, then KNN is activated and this layer becomes a KNN attention layer. Otherwise, it's an XL attention layer, and we're just following the initialization of each class here. And so that's kind of the main interesting component here. Otherwise, we need to initialize the feed forward block, and then we'll write the forward pass. So the feed forward block, just like it is up here, it's a residual, a layer norm, linear activation, dropout linear, and add the residual back in. So we just initialize all of these layers. The residual will be taken care of outside of the feed forward block. And in Torch, you can basically stack these different functions in a NN sequential. And so there's sequential and module list. And these are the two main ways you'll see Torch operations being stacked together. The difference is sequential, you don't need to call anything. If you call sequential, rather, it will just pass your data through every single layer. Whereas module list, you do have to actively say for component in module list, X equals operation on X. So this functions like a single operation, and module list is really just a list. So here we don't need to do anything interesting, so we can just call sequential. These just follow one after another. There's nothing we need to take care of in the input or output. So now we have the forward pass, and this part is just going to remember take care of the residual, layer norm, attention, and add the residual back in. So what I've done is copy residual as the input, and then we just process this through our layer norm, and then we have, remember, attention returns both the attention and new XL memories, and we add the residual back in. So we'll hold on to this and we'll return it at the end. But for now, we're not done with the forward pass because we still need to hit the feed forward block. And once again, the pattern is hold on to a residual, pass it through, add the residual back in. And there we go. And what we return is both feed forward out, which is the computation of the layer, and we've held on to these new XL memories, and we'll pass those out. And so when we build the outer layer of our model, rather when we just build the outer loop of our model, we'll hold on to these new XL memories and make sure we pass them in at the next segment. So that's our first stab at a block. And now let's move on to the model itself. Okay, so where should we begin with the model class itself? Well, first we need to initialize the parameters that tell us how big the model will be. So what's the embedding dimension, how many layers, what are the max KNN memories, how many heads, these kind of things. So I've already got that here, and there shouldn't be anything too surprising. And you can change what goes in here and what has a default value. You can configure as many things about the model as you want here. And I think I've left a few things out, so some details of this model are maybe a little hard-coded into the classes. But if we wanted, we could go back and, for example, we could really ensure that if we change the number of heads to 16, that that is appropriately passed into every single class. So for now, we'll just work with this because we've been using the same kind of parameters everywhere. And later we can really make this as flexible or as robust as we need. But for now, we just want to get an idea of how we built this. So initial parameters, and then we initialize them into self so that we can pass it through everywhere in the model in the forward pass. And now we need to remember to initialize certain weights and embeddings. So we don't want to reinitialize them every time we call it. We need to make sure that, for example, the relative position embeddings, or the embedding matrix, or the KNN, we need to make sure that we have one, and that's used throughout our model. It's initialized with the model and used at every call. So I've done just that. Here we have relative positions, a relative position for KNN. This is separate. We just want a separate one here. And then an embedding matrix and the KNN. And all we have to do here is call head dimensions, heads, and max KNN memories, which we can actually, we'll look at later, and how we figure out what the max KNN memory should be. And so now it's time to initialize what the model itself will look like. And for this, we'll use modulist, as we were just talking about. And maybe you'll get a better sense of the difference between nn.sequential and nn.modulist here. Because the purpose here of modulist is that inside of each of our layers, we need to actually make some configuration changes. And when we call it, we'll need to add in and pass in different things. So here's what I've got for our first pass at the model. For ion range self depth, and depth is the number of layers we want, we're going to go and follow the paper, excuse me, and say that the second to last layer will be a KNN layer. And otherwise, none. So everything else is an XL, just a plain XL attention. And then we append this, and we've picked out this appropriate parameter of saying whether or not the attention is KNN or regular. We wrap it in a block, and now we'll have 12 blocks in our module list. And the second to last one will be a KNN. And so when it's time to call this, we just, in the forward pass, we'll just call for layer in layers, and then we'll pass in the appropriate things. And lastly, going in order, we need our logits. So we need to initialize another layer that will basically take, once the computation is done, it will take these and spit it out into an embedding dimension by vocab size layer so that we can actually determine what is the predicted token, and then we can run our loss function. Okay, so that's the initialization. Now let's go on to the forward pass. And so obviously I've built this before, so I've already thought ahead about what these are. And my advice that we used earlier stands, that build the simplest version possible, so maybe you would exclude these, and then you would add them in as you realize they're needed. But for now, I'm just going to walk you through this pretty fast. There's not too much insight I can provide in how you build this, it's just putting all of the pieces together. So we do remember that for each of our blocks, we'll need to provide relative positions, XL memories, and labels during training. And so we'll initialize, during the pass. This is just to help us account for variable sequence lengths. We have the relative position and relative position KNN. So we've taken our initialized embeddings and we actually just call it. And this is the same as calling our relative position classes and getting the embedding matrix, rather the relative position embeddings out. And now this is really the only kind of tricky part of our forward pass. It's just making sure we're managing the XL memories appropriately. So if XL memories is not none, meaning we're in the second or onward chunk of a document, so we already have XL memories, then we don't need to do anything. But if this is the first chunk of a document, we're just going to initialize XL memories as 12 layers of none. And this is because when we pass in none as the XL memories, we've already built in the logic into our attention classes that says, if it is none, then really we just perform attention without them, and we're okay. We get what we need out of it. So that is sort of the switch that we provide, is saying whether or not it's none or whether or not it's already provided. We'll create an iterator, and this will just help us pass in to each layer the appropriate XL memory. And now finally we can move on to our input, which will be tokens X. We pass it through the embedding matrix. And lastly, we need a place to store new XL memories. I'll put that up here, just so all of the XL memory management stuff is up here. So at each pass, we'll pass out new XL memories, and we'll store them here, and that'll get moved on to the next segment. But anyways, this is the first time we're seeing our actual data. It gets fed into an embedding matrix, and now we call each layer of our layers. So this is the module list. We're saying for index and block in layers, if int is depth -2, then we're passing in relative position KNN. Otherwise, we pass in regular relative position. And the output is X and XL memory. So pass into the block our layer relative position, which can change depending on whether it's a KNN or XL attention layer. And we pass in the XL memories. That's what the next XL memories iter is doing. It's saying at each layer, I'm passing in the appropriate one. If XL memories is not none, then we append this to new XL memories, and we hold on to that for the next pass. And we'll see that in the outer training loop, how we manage that. Okay, and then we finish the computation of all of our blocks. And then we just need to take the computation and put it into logits. And then we just have a little switch here to say we're only going to focus on training. You could have an inference output. But we run loss, cross entropy. We have to rearrange the logits. We match them against the labels. And then when all of this is done, we return loss and new XL memories. And so for the next chunk, the new XL memories will be fed in up here as the XL memories. And again, that's managed in the training loop. And in both instances, we return loss. So that's our first pass of the model. Again, I've built this before, so I've already thought about this. It took me much longer when I was building it, but this is the idea. There's not too much insight I can provide. You just need to remember to do everything and take it step by step and make sure that at each call of a different class, you're paying attention to, for example, relative position. What do I need to initialize when I call that? What gets passed into the forward pass, and what does it return? And if you hold on to those three pieces for each class you've built, it serves as a very good guide, and you can just make sure that all of your ducks are in a row. So we've got our first pass in a model. Now I'm going to put all of our classes together, and we're going to try running the model. And things will go wrong, so I'll debug it, and I can come back and talk a little bit about what we've done. But in general, as this applies as sort of a principle of building models, you'll stick everything together, a lot will go wrong, and you just need to go through and debug the things one at a time. So wish me luck. Okay, as promised, 10 things did go wrong, but luckily nothing took too long to fix, and in general, torch stack traces and error messages are pretty good. So I'm going to go through the things that went wrong, and if you're a true completionist, masochist, and you want to hear about other people's software bugs, then you can stick around. Otherwise, you can jump to the next section, and this code will be online so you can see a completed working model. Okay, so what went wrong? A lot of things are something like you forgot to initialize calling self here, or self here doesn't exist. So a lot of small things like that. I think I was passing in relative position values into the init, rather the initialization of attention, but we only need it in the forward pass. So there's a lot of little things like that. Nothing too interesting. You get the error and then you go fix it. Let's see. So as discussed, we did have to fix the training loop to account for, or rather, we fixed not in the training loop. This case where you're on the first pass of a document, so you're dealing with the first segment. We had to build some logic into the KNN attention class. And this is just an if switch to say, if the KNN has no memories yet, then skip all of this, because there's nothing there. And you can just do regular QKV. So this just reverts to an XL attention class. Otherwise, if there are KNN memories, because it's the second pass and, for example, we've added it, then go through the appropriate, kind of as we've discussed, KNN attention. Okay. And then, what else? In the training loop, something did come up where when you're doing the chunk size, you have to remember to add 1, because you're splitting these things out, and then basically you're shifting your sequence data and label data over by 1. So you actually need 1 additional token to account for that. Let's see. We did move the attention type out of the block. So here, I just found it easier and a little simpler to call attention type. And you pass in whether that's XL attention or KNN attention inside of the model rather than in the block. So the block is just a bit cleaner. And inside of here, you pass in what the attention type is. Rather than just having a flag, we just pass in the attention directly. A more subtle bug that was harder to figure out is, let's see if I can find it. It's detaching the XL memories so that they, I have to look for detach, so that they don't, right. The error message here was a little strange, but basically we've created the XL memories and they're part of our computation graph, but then we need to hold on to them and we don't want to backprop through them, we want to stick them into the next segment of our training loop. So you need to make sure to call detach, otherwise the graph doesn't really know what it's supposed to do. So you have to remember to attach these. And similarly, this happens in, as expected, in KNN, because remember in our KNN class, there's a lot of torch data comes in, and then face only works with NumPy, and we're using a NumPy database. And so you need to make sure to detach everything from the computation graph, convert it to NumPy. When it goes back, you need to make sure that it's turned into a torch tensor. So there's just a few kind of data type formats going in and out of the KNN. It's important to pay attention to. Let's see. The PyTorch einsum has different syntax than einops einsum. So if you remember when we talked about einsum, it was always of the format, Let's see if I can find an einsum example here. So einops einsum, you always put the variables first, and then the Einstein notation docstring after. This is the einops format. If you use torch einsum, which I was accidentally importing, these go after the docstring. And so you just need to be explicit about which one you're calling and which one you're using. So you might have seen some discrepancies in the code throughout, but these are things I've cleaned up, and now the model does in fact run. Okay, the model has been debugged and now it's running. So if you remember from an early section, I believe section 2 of the video course, we created a training loop. And so I've basically just copied that here. We're using the archive summarization dataset, and we're converting these into, remember, these large chunks of, say, 10 segments by 512 sequence length. And so we have this long document, split it into 10 segments, and feed them through one at a time, so that our memory is relevant, because it's all connected to the same document. So that's just a refresher on our justification for this training loop and this data set. Here we're calling memorizing transformers instead of our fake model, which was just a random sequential kind of model. And the only thing to note here inside of this training loop is that we make sure before each iteration, and this is one of our chunks, we clear the KNN memory and we clear the XL memory. And then we pass these in here. And so we have the large 5121 length segment, we chop it into 10 segments, and we feed it through. And so at each step I've got us saying segment complete, just so we can keep a track, because it's kind of like having 10 iterations inside of each iteration. And we have a validation loop here. And here we go. This will be one long document completed. We go through each segment and we compute the training loss at the end. And so, great, we've built the model. It's running. It's doing what's expected. However, it's incredibly slow. So obviously what we've been missing is GPUs. So now we'll look at how to take our entire model and put it on a GPU. And for this, I'm just going to use a free Colab. This works with a T4 GPU. So we want all of our model weights and we want all of our input data on the GPU. And we need to make sure that, for example, all of the KNN that's going on the CPU stays on the CPU. So we basically need to make sure that things are moving between hardware devices correctly. So let's take a look at that, and I'll show you all of the changes you need to make to basically put this on a GPU. All right, we're back, and we've changed the runtime. So at least in Colab, and this won't matter if you're using a different platform, but you can change to a GPU, and I believe in the free tier you can still get the T4s. So all you have to do is change the runtime, and then we'll go through a few of the changes you need to make to the model in order to get it to run on the GPU appropriately. So I'm just running an end-to-end GPU set of cells here. We check our GPU with this command, and then you can see, great, we have a Tesla T4. And when you call device, you basically want to store the CUDA device in this variable. And then throughout the model, you will pass this in. And so I've just made this block of hash marks here wherever we've made a modification where essentially we're just passing in device equals device. So this is relative positions. You need to make sure that during the forward pass, it appropriately goes onto the correct device. So just earmark this in a few places. As I just talked about, in KNN in particular, there's a lot of moving back and forth. So here we're calling detach CPU numpy because our data is coming in and we need to move it to a different device, detach it from the graph, and convert it to numpy. So you just need to make sure that you do all of these operations, otherwise you might get a sort of confusing error message. We do that here, here, a few more places, and in our attention classes, you just get the device associated with your inputs. So here's your text. You hold on to it, and then you pass it through. For example, the mask also needs to be on here. So there's just a lot of little things where you need to remember to put everything onto the correct device and make sure that you have this device equals device. And that is that's about it, except for this, something I wasn't aware of. In our previous definition of block, and this worked on CPU, we were calling norm here and initializing it here. And Torch really doesn't like that, so you have to initialize it at the init. So we made self.norm, layer norm, and then we call it, and things work appropriately. Great, so no other changes here. And then, of course, you need to remember when you're initializing your model, put your model also on the GPU. And that should be about it. I added a few print statements in here, and our model is already running. So we can see what's taking time, because I already know for a fact that the KNN searching is going to take most of the time. And in fact, we look, one pass through these 10 segments takes about 17 seconds. Most of that time is just spent on begin KNN operations, end KNN operations, time taken 1.8. So it increases each time because our KNN memory is getting longer. So at the 9th segment here, it's taking almost 2.5 seconds to perform the search, retrieval, and addition. So clearly the way to get this going faster is to modify the KNN to be much faster. And we can look at a lot of different ways for doing that. But for now, we've got our model running. It's going not fast, I would say, but it's working. And where's our loss? Our loss is going down very slowly. Okay. So, great. We've built a model end to end. We've put it on a GPU. And from here, we can do a lot of different things. So, for example, using a different index, smaller max memory, one index per batch, as the authors originally proposed. There's a lot of different options that we discussed a bit when we were first building the KNN. In addition, we'll actually want to test how this model does. So that was the whole point of doing this. We want to see if it does what it should be doing, which is using past context chunks to better condition current outputs and inputs. So are we able to look at past sequence chunks and appropriately pull that context in and make our outputs better? So we can design a lot of experiments to see how well this works against other architectures, like just a basic decoder architecture, and see how the XL and KNN memories are affecting the attention scores. So we could actually look inside of the model and see what's actually going on and how well they're helping to condition the new outputs. So there's lots of broad optimization to do and lots of experiments to verify and see if this is doing what it's doing, but we can revisit that later. Give yourself a pat on the back if you've been following along with me. We've created a really interesting, non-trivial model, and line by line, you can kind of probably look back anywhere in here and say exactly what's going on and why it's going on. Even if you never want to do this again and you're happy just calling Hugging Face models, nevertheless, you have a good understanding of what's going on underneath the hood. So this will help you become an expert in building, training, and understanding large language models. And best of all, we've covered a huge range of modern deep learning topics along the way. So we looked at self-attention in detail, recurrence, retrieval augmented generation, vector database management kind of things, positional encoding, and we've gotten deep into Torch details and seen some finer points of the research and theory along the way. So really, I hope you've come away with a deeper understanding and a huge number of new tools and some new things that excite you that you're going to look deeper into. So I hope you use these tools to build lots of weird and wonderful things. And that's all for now. I'll see you next time.